A very good morning to everyone. Today we are going to study about why we prefer extended sources in Newton's ring and the experimental arrangement of Newton's ring experiment, and at the last how the Newton's rings are formed. So first of all, before moving to the extended sources part, I will explain what are point sources and why we prefer the extended sources rather than point source. So in case of point source, if we consider a thin film of uniform thickness or non-uniform thickness, and that film is illuminated with monochromatic light. And if the film is illuminated with a monochromatic light from a point source, then what happens? The light is reflected from all the corresponding points of the film. For example, in this diagram, I have shown only 2 points, that is point A and point B. When it is illuminated with this monochromatic light and light is reflected partially and partially refracted from points A and B, then these rays does not reach the eye simultaneously. So in order to see the interference pattern, we have to move our eyes in order to see the whole film and their interference pattern. So this is the drawback of point source. That is, in order to see the pattern, we have to continuously move our eye from one point to another point to see the interference pattern. But in place of point source, if we consider an extended source, then the benefit of extended source is that if the point A and B and light is reflected from point A and from point B, then the reflected rays 3 and 4 emerging from point A and the reflected rays 5 and 6 emerging from point B, all the rays can be viewed simultaneously through our eyes at one place. We don't have to move our eye from one place to another place to see the interference pattern occurring between the ray 3 and 4 and 5 and 6. So this is the benefit of extended source. That is, we don't have to shift our position of an eye to see the whole view from the film. And in the Newton's ring experiment, we prefer the extended source rather than the point source. Now the question arises, why we call it as Newton's ring experiment? The reason behind is the whole experimental arrangement and the outcome of this experimental arrangement, that is a circular rings of alternate dark and bright pattern, was first being seen by Newton. So that's why this experiment is known as Newton's rings. So in this experimental arrangement, we consider a monochromatic extended source which I just now explained to all of you. So extended source is used, and that is sodium lamp is over there, and light from the sodium lamp is rendered parallel on a thin transparent glass plate which is placed at an angle of 45 degrees to the incident beam. As soon as the light falls on the glass plate, the light is partially reflected towards the downward direction. That is shown by this arrow. So in the downward direction, we see that a plano-convex lens denoted as C and a plain glass plate which is denoted as P is placed. The plano-convex lens is placed on this plain glass plate. So the light from this thin transparent glass plate G falls normally on the plano-convex lens and plain glass plate. And after falling on this plain glass plate and the plano-convex lens, the light is reflected back and the image is viewed through a travelling microscope. So in this microscope, we see the alternate dark and bright circular fringes whose center is dark. That is concentric circular rings we observe in a travelling microscope. So this whole phenomena was first seen by Newton's. That's why we call it as a Newton's ring. Now, next point we will explain basically how the Newton's rings are formed, and that's to a circular rings are formed. So formation of Newton's ring. So basically the Newton's rings are formed at the plano-convex lens, which is denoted as C, and plain glass plate, which was denoted as P in the previous slide. So that portion I will explain again. So in this case, we see here L is my plano-convex lens and G is my plain glass plate. So light, that is AB, is the monochromatic ray of light which falls on this system. So a part is reflected from point C. This point C is the glass air boundary, that is, this is the lower surface of plano-convex lens and this is the upper surface of my plain glass plate. So from point C, the ray is partially reflected along the ray R1 and partially it is refracted along D. As soon as the ray reaches the point D, it is again reflected and it emerges out in the form of ray R2. Now in this case, the Stokes law is applied, that is, a phase reversal occurs. Now the question arises, where this phase reversal occurs? The phase reversal occurs at the point D rather than at the point C, because if we see the plano-convex lens, then plano-convex lens, this acts as a denser medium. This is an air film which acts as a rarer medium. Again, we have a glass plate which acts as a denser medium. So if I consider the point C, then from point C, the ray is reflected. So this reflection part is from the surface of rarer medium. So phase reversal does not occurs at the point C. Whereas when the ray is refracted and strikes the point D, so at the point D, we can see that this is an air film. Air acts as a rarer medium and this glass plates acts as a denser medium. So from point D, the ray is again reflected. So this is reflected from the point D. So the phase reversal, or we can say the path difference of lambda by 2 is applied at this point. And both the rays R1 and R2 are emerging from the same monochromatic source. Both the rays are coherent and they will superimpose and will give rise to an interference pattern. And that interference pattern we basically see in the travelling microscope. So if I see this diagram at both the sides, that is this side and this side, it forms a structure of a wedge-shaped film. So both the sides we have a structure, or we have a diagrammatical of picture of wedge-shaped film. So the path difference in wedge-shaped film is given as 2 mu t cos r plus theta plus minus lambda by 2. We write it over here. And this lambda by 2 term comes here due to Stokes law of reflection, which is occurring at the point D. You can write it plus lambda by 2 or minus lambda by 2. It is completely your choice. So this I denoted by equation 1. Now in this whole experiment, we have a normal incidence. If we have a normal incidence, then angle I is equal to 0 and R is equal to 0. So I is equal to 0 and R is equal to 0. So my cos R plus theta term will reduce to cos theta because R is 0. In addition to this normal incidence, here the angle theta, that is this angle, this side angle theta and this side angle theta, theta is very small. If theta is very small, then cos theta will be equal to 1. Under this situation, the equation 1 reduces to the form of part difference is 2 mu t minus lambda by 2. 2 mu t minus lambda by 2, that is equation 2nd. And at the point of contact means where the plano-convex lens L meets the glass plate G, that is this point O point. At this point of contact, the thickness is 0 and the thickness gradually increases as we move away from the center on both the sides. So at the point of contact, thickness is 0, so part difference is equal to lambda by 2. And this equation 3rd is the condition of destructive interference pattern. Hence, in Newton's ring, the central spot of the ring is dark. So, if I want to give the condition for constructive and destructive interference pattern, so for constructive interference pattern, the part difference should be an even multiple of lambda by 2. That is 2 mu t plus lambda by 2 is equal to 2n lambda by 2. That is 2 mu t is equal to 2n minus 1 lambda by 2, where n starts from 1 to n 3. That is equation number 4. And similarly, for destructive interference pattern, the part difference should be an odd multiple of lambda by 2. That is 2 mu t plus lambda by 2. This is equal to 2n plus 1 lambda by 2, where n starts from 0, 1 to n 3. That is 2 mu t is equal to 2n lambda by 2, that is n lambda, where n will be equal to 0, 1, 2 and 3, which is the condition for destructive interference pattern. So from equation 4 and 5, it indicates that for a particular dark or bright ring, the thickness should be constant. Every fringe is the locus of point having the constant thickness air film enclosed between the convex surface of the plano-convex lens and glass plate. These loci are concentric circles with the center at the point of contact of the two surfaces. Therefore, the fringes are circular with its center at the point of contact. Hence, the fringes are due to equal thickness in the shape of concentric rings with point of contact of the film at a center of the rings. Now, if I see the equation 4 and 5, in the previous slide, I have used the minus sign and here I have changed to the plus sign. It is completely your choice. You can write minus lambda by 2 or you can write plus lambda by 2. Thank you.